So last time we looked at the pollutants, and today, before we start the class, I want to ask you, what do you think are some of the factors, natural or artificial, that can reduce outdoor air pollution, and what are some of the factors that can increase the outdoor air pollution? And yeah, like the natural factors. For example, the hint that I can give you is dilution. Dilution. Pardon, say it again. The national capital decrease, increase. Okay, right. So let's be a little more specific. Yes, Parveen.
Proper waste management.
If there's proper waste management, then that would decrease. Yeah. So if there's proper solid waste management, then maybe the methane emissions would decrease. But the natural factors, not the management eye, but the natural factors. Yeah, so naturally there are processes that can increase the air pollution. Yes. Yes, so naturally there are bacteria that do a wonderful job for us, but also at times cause nuisance. So yes, Hanya. Yes, absolutely. So carbon cycle, which occurs naturally, right. So anybody else before I move to the answer? No? Okay. So let me tell you what it is. Basically, I'm trying to build a case for naturally what are some of the components that are there, and how do you think that they could contribute? So we talked about the particulate matter, right? There are pollutants that occur naturally. But if their size is around 10 micrometer, gravity naturally can help those particles settle. So the closer they are to the troposphere, it is yes. And then rain. So whenever there's smog, we just hope that it rains so that it can wash away all the particles. These are all natural factors. We're not doing anything to it. Winds, I think it's particularly for polluters, factory-onyx. It's important that the wind just takes the pollution out of their sight, out of people's mind, and then they don't need to do anything about it. And chemical reactions. So we saw how, even though, like, if we look at it from this angle now, when the SO2 is converted into H2SO4, it can be removed from the atmosphere. So in a way, that natural process or the natural chemical reaction is a way of removal of sulfur dioxide from the atmosphere. And if you look at the increase, it can again be because we have, so everything opposite of that. So because we have built a lot of buildings, if there are hills or mountains that do not allow for air to take these pollutants away, they could build up in greater quantities close to the troposphere and then impact the plant or the plant. And similarly, some of the natural causes, like we said, a lot of plants produce, so a lot of plants produce volatile organic compounds, and sometimes over forests, there is this big case that people do not understand. Why would you find such things in natural scapes? But naturally, because they release VOCs, they could end up causing increased air pollution. And last time, and we haven't talked about it a lot in this class, but last time, a lot of students asked me why microplastic pollution is found in the Antarctic, or why pesticides are found in the remotest of places. How could the CFCs travel to all the way over the Antarctic to decrease the ozone layer? So I think that comes down to first the reactivity that we talked about, that let's say chlorine is the most reactive halogen, then it has the ability to multiply and then reach out. Those are very reactive reactions. They happen at a fast pace. They have the ability to move away from where they are produced. But also because of the wind and all of these natural processes combined, the grasshopper effect is when it can travel from one place to the other and then hop off. So let's say it settles in one place and then another wind or a water body takes it away with itself to a place that is farther than the source, and then it can go way beyond where it was. And temperature inversions is simple to guess. I'm sure you've already guessed it, but sometimes over cities, and I hope we'll talk about Bhopal disaster at some point. Sometimes over cities, what generally happens is that the warmer air rises and it's replaced by the colder air in the city. So that's how we instantly have winds gushing in. But at times, the warmer air, when it rises, so the natural mixing should take place. But at times when the warmer air rises and the cooler air comes down, they do not mix. And the warmer temperatures generally allow for a lot of the reactions like the smog to take place. So it is aided by the temperature that the sunlight, for example, provides. So when that happens, you just see this thick. So above it, it's all clear. So for example, when you're flying above Lahore, you'd often see these inversions. That's precisely because of the same factor that the air refuses to mix, and it's a natural phenomenon as well. And those inversions also cause increase in outdoor air pollution. So, which then brings me to weather, and because we're going to relate it to climate change, can I finish this part and then I'll get to, you raise your hands to let me know that you have questions so that I can come back to you as soon as I finish this section. So weather is short-term conditions, and there this temperature, the air pressure, all of these factors contribute to what the wind would be like. Of course, the sunlight, the intense the sunlight, the more warm it would be. So all of these factors contribute to what the day-to-day weather is going to look like. And we know all of this. And like it says, most of it develops in the troposphere and most of it stays or impacts the troposphere. So just keep that in your head, and then we'll look at, like I said, these natural, these components that measure the weather for us, they are shorter. So let's say your daily. So last time I shared a video with you because I personally I love how the weather pattern changes and how when the weather forecasters tell us what's going to happen and what's the pressure and how that is predicted. And the video essentially was telling you how they predict those and what are some of the signs that we should see for or look for if we want to know whether it's going to rain or not. Anyways, but these are the factors. So humidity, we said, okay, so if the air is humid, it could be warmer, it could make it more uncomfortable for us. If the temperature is more, depending on where we are. If we are in the UK, we would love a nice warm weather. Pakistan would probably run away from the warm weather. But all of these, like I said, the solar, so all of these contribute to the weather that we get. And that impacts our mood, but that also impacts growth. That also impacts how life particularly produces growth. And if we measure the same quantities, the same things for like a longer period of time, then that is climate. That's so over decades, over years, that monitoring would not be weather. It would be the climate of that particular place. And that they can be localized. We can say that the climate of Pakistan, but the same data is also contributing to the global climate. So all of those patterns you see on how things are changing around the globe would also then give you a lot of information. It's important for us to know it, I think, because we want to know what's going on and what will happen, because with climate change, the uncertainty has increased, and that doesn't help us because then it impacts the wildlife as well as our own life, the way we operate. These are, I do not want you to go into this in a great detail, but it's nice to know where some machines that are doing this for us. And now we have this simple weather stations that have all of these factors in one. And hopefully, if we go to the lungs fields for our agriculture-related discussions, I'll show you the weather station that WIT has developed and the soil moisture sensor that WIT has developed. Some of the things that are there, we'll also get to see them, and we'll talk about why it's important to. So some of those instruments are old instruments, and it talks about the units, but again, we need to monitor this, so we need to know what instruments are there for them. And again, not to get into the details because I'm going to teach some of this to you later. We already know about DO, we have an understanding of pH. But measuring the temperature and pressure tells us what the clouds, about the cloud formation. Of course, cloud formation would contribute to precipitation. And precipitation would lead to floods or droughts, depending on whether it happens or not. And all of those events in the long term impact our food security, impact land, which is why it's important that we measure it. And how do we measure it? Do you have an idea of how do we measure our long-term climate? Yes.
Your data from the last century and comparing today.
Yeah. So essentially, this weather station that's at LUMS is giving us the day-to-day data for temperature, air pressure, wind direction, all of that for LUMS, right? So we are monitoring it through that. Imagine thousands of these weather stations spread across Pakistan, which would give you data that you can then monitor. And there's, of course, a dashboard that can keep all of this. So in Pakistan, it'd be the Met department that would do it. And then, all of those satellites that are there, they're now measuring it with great accuracy. And we looked at one of the satellite images or manipulations of a satellite image for methane in the article that we looked at in the last class. But we talked about weather. And like I said, the long-term measurement of weather for a longer time, just to understand what we are doing is climate. And that climate the control on that is going less and less, is now less and less in our control and more on unpredictability of it. And so scientists are coming together to make sure that they predict, forecast, prepare communities for what is to come, so that our natural balance remains. But let's start with what is climate change. So we've talked about naturally the gases that are there, which contribute to warming of the planet because they absorb heat. And some of those are mentioned here. I've highlighted water vapors because last time I didn't highlight it. And Roshan knows, as Han, who was the chemist in the group, held me accountable for not mentioning that water vapors also contribute to, are also a greenhouse gas. So water vapors in the atmosphere are also greenhouse gas. But we generally focus more on these because they're, the kind of damage that they've done is so much more, and water vapors are needed for our water cycle anyway. So yes, they're always there, but they have an important role to play in the water cycle, which is why often you would see us just talking about some of those gases. Okay, and then what's the impact that it's causing? The impact is varying. As I said, in my own lifetime, I've seen so many events, it's scary. Like when I started studying it, when I was your age, things were very scarce, like events were very scarce. But this summer you saw how many events took place instantaneously all across the globe. And so many events have taken place, even though we haven't been most active around the world. And I think that's why it's important for us to see what's going on. But before I take you further, some of you might ask, why is it so important for Pakistan? And some of you may have read that Pakistan is the 6th most vulnerable country, or always in the top 10 country. But that figure changes depending on what sort of events take place. If there are more floods, it's generally the coastal countries that get impacted, or islands that get impacted. But if you look at this climate hazard risk data, which is of comes from a German watch. They always, like for the past few years, Pakistan's always been in the top 10. And that tells us that we should be prepared, that we have a high risk, that slight changes in the climate would cause climatic events that we may not be able to control. And the degree of prediction also would be very, very weak. But if you look at our contribution, like I showed you last time, if that's the contribution of the world in terms of carbon dioxide, then this is where Pakistan is. So it does not matter how much we contribute to it. Climate change is a global phenomenon. And like we said, just like those pollutants can travel from a place where they're produced to a place where no human resides, these impacts similarly then travel to places. And it doesn't matter what your contribution is. The fact remains that we're going to be impacted by it the most. And so we should be prepared to take care of it. How do we monitor it? So this was my question. And some of you answered it in the previous question that I asked. Mostly through satellite imaging now, and mostly through GIS or the Geographical Information System, where a lot of these satellites are just traveling above in the mesosphere, or between stratosphere and mesosphere, to tell us what the solar activity is. So remember the parameters that we needed for weather. Essentially, those are the things that we measure. Sometimes they measure the gas that they want to monitor, but these satellites with each passing year are becoming also more diverse in what they can monitor. So I think I added an example. So this particular image just shows how, and I call it like atmosphere-ocean interaction. So it basically shows what the temperature of this water body is. And we're not going after what is causing the temperature to increase in one place compared to the other, but the fact that a profile has been created for us, and the profile tells us that it's warmer in some places and it's cooler in the other, not too distantly located from each other, tells us something is changing. And that change then allows us to monitor. If, for example, there's an industrial waste, let's say a factory is throwing all of its nuclear waste here, then that could be an indication. If it's not supposed to be like this, then we sort of go and find out the root cause of what's going on there. So I think that then brings me to all of you. And I'm asked very often, why should the non-scientists be bothered? And I sent you a video yesterday, and I'll send you another video again of one of my favorite speakers, of an artist working with scientists to display the change that is happening and the awareness, like how their lens then brings more awareness to the public. So when you have time over the weekend, please do watch that video. She's essentially an artist, and she uses all of that science data and those different ways of measuring things and displays it in public spaces for behavior changes, able to scale the changes that are happening. And it's not just the science. So basically with this slide, I want to tell you, it's not just the role of a scientist. The scientist to create the change, it's all of us. Because sometimes in the science language, we say sometimes it's the photographers who have created more change than any scientist can create. And it's because seeing is believing, and a lot of climate science data that we produce that people don't read has lesser impact than one powerful image that can go viral and get video of how severe the situation is, particularly, for example, for things like plastic pollution. So for example, I want to tell you that all of you have a role to play in combating or in adapting or mitigating climate change, and you just need to be made aware of that as an individual who holds the power of future. We're going to be talking about air pollution control later anyway, but basically what I want to tell you is it's possible to move from this to this, and researches have been done, devices have been made, and we'll talk about how they function, and what kind of instruments are used, or what kind of gadgets are used to control the pollution or the smoke that would release into the atmosphere. I think I can stop here for this lecture and maybe give you the chance to ask questions about this before we move to the next section. Yes. Okay, let me come to you because I could not hear it. Okay. Can you say it again? Yeah, maybe I didn't put it right. So basically, by wind speed, I next look when the wind is traveling or the wind is blowing, it automatically takes the pollution away from the source, where it also dilutes it. So if it was concentrated here, the moment it blows it away, it's mixing with the air and you don't see it anymore, and it's there, but it's diluted. So it's not visible to our eye. When I mentioned wind speed in the increase, I was essentially saying that the reduction in wind speed increases our pollution. And that reduction is caused by building these tall buildings that stop from the wind to come and mix here close to where we live, as well as the hills. So some of the cities, some of the countries, some of the places that are mountains, they might stop from the hills. Might, I'm not saying absolutely, but they could stop the hills. And that would result in increase of, no matter how slow the increase is, and that's something that we also look at today. High concentrations, shorter time, that impact, and smaller concentrations building up over a longer time, and that long-term exposure could have the same impact on it, even if it's diluted, because the exposure has been so long, the impact could also be the same. And we'll look at it today. Great question. So I think last time मैंने बड़ा chemistry के साथ explain करने की कोशिश की and it didn't work. So the example that I give with this is that let's say a pollutant is going in. So it is as similar to brushing, you know when we rubbed the brush and then it created charge, or the balloon. So essentially it's static. It doesn't have any charge. But when you rub it, that surface becomes negatively charged. So just by applying the little bit of pressure, we now allow for the static charge to emerge. And then when that, let's say, it's not the pollutant, it's not the smoke, it's the balloon. And that balloon now goes against the wall. Basically, it's friction here does it. We build those static charges that we use to build the pump or the balloon, which is built in this device, and it allows for these charges to then go and find. I learned the hard way, so last time I couldn't explain it. Okay. All right. So I know you're probably like overwhelmed because it's quiz day as well, but I assure you it will be fun. And a lot of you are going to do a lot of this. Like I will have very little part in this lecture. You're going to tell me what's happening here because you've already seen it. So the lithosphere, we covered it in lecture 2. And because you've revised it already, I hope that you'll be telling me what it is. It's that topmost layer where most of the life resides. We'll also look at some of the cycles because that nutrient cycling is important for the biosphere. But we've looked at this already. So what does this tell us? Yes. The 3 layers of here, yes. And then it's divided into the core, the mantle, and the crust. Now the fun thing is that 30% of the weight lies here, 68% of weight lies here, and only 1% of the weight lies here. So it's only that 1% where life is residing. In terms of mass, most of the mass of Earth is just there. the lithosphere actually comprises of a very small percentage. And if you also remember what we looked at in lecture 2, we said that that lithosphere is divided into oceanic crust. So we call it crust, but it's divided between oceanic crust and continental crust. So, for example, if you look at that cross section, it will show you where the continental crust are and where the oceanic crust are. And we've already, this is why I wanted you to learn about the tectonic plates and everything. So these then form these crusts divided into chunks basically along certain tectonic plates, which is flowing over these mantle or the more fluid part, so that we can, we can survive on the planet. And this is then the most interesting part because we're going to relate it to food production as well. Although like this layering is complicated, and again, I'm not interested for you to know what it is called. So here it's simply O, A, B, and C, where it says there's a parent material, that parent material weathers, and then a subsoil is formed, and the subsoil is weathered, and the topsoil is formed, and as organic matter falls on the subsoil, more nutrients are added. So there are some natural nutrients that are there, which come from the weathering of the rock, because rocks also contain a lot of minerals. But then there's a lot of organic matter that's now falling on the soil and also nutrient content. If you look at it, it will also show you of the biodiversity on the topsoil, but also of the biodiversity under the soil. So I think what's most important, and I generally say that when you move from here to here, you're also moving from the north of Pakistan to, let's say, Punjab. Because the soil here is more mature, it's more fertile, it has more nutrients compared to as you move up north, because they're closer to the mountains, and the soil formation takes a lot of time. Which is why people will tell you that losing the topsoil is it's a non-renewable resource because it takes such a long time for weathering to take place. And we will say the same for Phosphorus Cycle, which forms by the weathering of the rocks, that it's a slow process. And that's why we value our topsoil very much. And once we lose it, we kind of lose it. Is there any question that we have for the layers of the soil? It's fairly simple, but keep it in mind because we'll be. But then also look at the role that each species play. By digging these holes, if there's fungus, by creating those vents, the bacteria that fix nitrogen, which we'll talk about. So all of them have very important role to play in food stability, but also in the biodiversity of the soil. Awesome. Now let's look at the soil types. So how many of you, when you look at the soil, think of the various types I think we all do because we, since childhood, say this is clay, this is sand, this is silt, or generally, for example, with dams, we say a lot of silt is very bad with the dam. So that's basically varying sizes. And those varying sizes then give different characteristics to the soil on how water could percolate down. But the one thing that I think I want you to remember is that the soil is alkaline in nature. It's not acidic, it's alkaline. And you can also already start thinking about what kind of elements will be found there. So calcium, magnesium, because they form calcium hydroxide, So those are the components that are more about. Any question? Awesome. So just the sizes, essentially, that's what's changing. But then that contributes to holding the soil together, holding water on the topsoil. So for example, if it's sandy, most of the water will go to the ground rather than staying on the surface. So that also is important for you. But then in environment, we generally talk about, it's not always straight ahead, these three types. It's actually a combination of those. And a lot of times for example, we'll look at the environmental impact assessment and they'll talk about the soil type. And they often use like sandy, gloomy soil or silty clay soil or just gloomy soil. So it's basically a combination of all of those. And that then defines that it contains a percentage of each. And then again, vary in the organic matter. That's there. And that tells you about the type of soil and what would happen to the soil. So we talked about pollutants in the other sections. We're now going to be talking about some of the problems that our lithosphere is facing. And one of them is acidification. So if you remember the last lecture, we talked about acid rain. And we said that that acid rain will go and fall, let's say, on a particular space. It could be both dry deposition, it could both come with the wind as well as just the power. That acidification, of course, is not good for the plant. And that acidification, like I said, can remove calcium and magnesium, which are important. So it can remove or leach some of those important components that are found in the soil. So that's one important thing. Then the other thing is that when carbon dioxide is released, we said that a lot of carbon dioxide is fixed and there's organic matter. But when that carbon dioxide is released in the subsoil, it can react with the moisture and form a weak acid called carbonic acid, which again is not good for the soil. So increased carbons also then that as well. So some of these things that we need to keep into account, that soil is naturally alkaline, and acidification, no matter how it happens, is not good for the soil. So you'll see some of these problems happening, and then I think there's one term that's called hydrolysis, which is pretty much the same, where the nutrients are leached away and the chlorophyll essentially is damaged and the stomatitis grows, so the plant wouldn't transpire anymore. So it's important for the plant to transpire to basically cleanse itself as much as moderate the temperature. Just an indication of those. The second most important one is desertification. So part of it is anthropogenic because we cut down the trees. So deforestation leads to desertification. Clearing the land for agriculture leads to desertification. But sometimes things like acid rain destroying all the life that there is, overgrazing of rangelands will also cause desertification. So there are multiple factors that then lead to the lands becoming naked. And the lands becoming naked is not good for the environment because it no longer fixes the carbon dioxide from the atmosphere. There's no longer life there. It no longer can contain your temperature, which is important for the plant. If anyone has any comments or any examples that you've heard of this, if you've heard about it before, please do talk about it as well. And the next is salinity. You must have seen it a lot around. Some of it is natural. Sometimes the groundwater is naturally brackish, and when that groundwater rises or components of those groundwater rise, there is salinity in the soil. But all the water that we are using for irrigation has a salt content as well. So while the water goes into the field, a lot of the salt remains there. So salt is generally building up as we irrigate the land. And that's also something that we need. So in the longer run, we'll have more salinity or more salt building up. And I put the values there for you to make sense of the scale. If it's 3 to 6 grams per liter, it's slightly saline, but if it's over 12 grams per liter, it's highly saline. But this is just the division in terms of what the salinity, high salinity, or between this medium salinity or low salinity or slight salinity would be. The water that we use to irrigate a field, its salinity or its salt content should not be more than 45 grams per liter. If it is in excess of that, then the salinity would increase. And the only way to get rid of this is to flood irrigate. Make sure that a lot of soil is now dissolved. Because sometimes people even remove the top layer or bring more soil just to make sure that it's taken care of. But the easiest way is to dissolve it into water. So flood irrigate it, get rid of there. And then water logging is also another problem, but maybe we can talk about that later. And you must have seen similar pictures for, if not any other place, the bio, which essentially means that if our soil becomes, maybe, so for example, in Lahore, we are claiming a lot of land that is suitable for agriculture, and we are converting it into urbanized land. Now we are creating a lot of these spaces that would eventually become, we're getting rid of that topsoil. And once that happens, then all we have is dust or the ability, and as soon as there would be wind, that those dust particles would just go there. Of course, this event would occur more in places that have more sand, sandy soil. But generally, so now the composition of the soil becomes, if soil is held together, if it's moisture high, will not have dust. But with increasing droughts, with increasing urbanization, with increased clearing of land, we'll have more dust storms. And they reduce us or deprive us of the topsoil, which is for the drinking of the planet. And I think somewhere in here I have inserted a link for a video of Gobi Desert in China, which is also increasing in concentration. So in terms of the space that it had, the Gobi Desert is now expanding. So desertification is also, we now say, a human phenomenon. So
can we store it somewhere?
Yeah, so a lot of times when we talk about pollution control, we talk about how soil was transported. Oftentimes you would have seen land that is being converted into agricultural land, like a lot of tractors bringing in fresher soil. That's basically, they're bringing better soil. Soil from some of those waste to the soil that's relatively unhealthy. Basically, all it needs is, such a mixture of the soil for the plants to be held, for the nutrient contents to be held, a certain organic matter content for life to thrive. But yeah, like a lot of practices just do it. How people do it. Like it's a general understanding, and I don't think we need to learn anything about it. How much time? Your president publishes it. Okay. So back to the nutrients. There are 40 nutrients that are essential for life, and out of them, 17 are most important, and out of them, 5 are more important. We saw in our research what those 5 elements are. Those 5 elements essentially form the proteins, are component of proteins, the nucleic acids, our DNA, which is why they're more essential to life. And I would encourage all of you to, even though I haven't put these here, encourage you to go and look at some of the structures for protein, what kind of chemicals it contains, just for you to make sense of where sulfur is, where carbon is, where phosphorus is. And if you remember the 3 principles of sustainability, we talked about the solar light or the sun. We talked about the biodiversity. The 3rd component was chemical cycle or biogeochemical cycle. So this nutrient transport between life and lithosphere that includes the atmosphere is really important. So essentially, biogeochemical cycling is the movement of these chemicals from the hydrosphere, biosphere, atmosphere, back to atmosphere. So that's the cycle that we're talking about. And just like we said, energy cannot be created or destroyed, matter also is kind of constant. So this chemical cycling is important for the planet because the same element then keeps coming back to where it is. And we have I think someone mentioned, now mentioned in the first class, that we have macronutrients, really important for our well-being because they make our protein, fat, and carbohydrate component. And then some of the micronutrients, which are also essential because And you must have heard like recently there are a lot of ads running for zinc and the importance of zinc for both genders. So like I said, it's basically the transfer of those nutrients. The cycling is the transfer of the nutrients between the biotic sphere and the abiotic sphere. So your biosphere and then the atmosphere, lithosphere, and whatever the atmosphere is, atmosphere. Okay, and now you will tell me what the hydrological cycle is, the most basic cycle. And this is generally where the biogeographical cycle discussion starts. So sunlight.
Sunlight causes water from oceans and rivers to evaporate, then that rises and condenses to form rain, and then rain falls and surface water, it permeates into the soil or it may run off back into rivers.
Absolutely. So that's hydrological cycle in one sentence for you. The only thing that you look at your books is how human intervention is increasing it. So how urbanization has now created impervious surfaces. So a lot of water does no longer percolate down to reach as groundwater, but gushes through towns, comes together and floods our drains and rivers. So in these cycles, it will also show you what the human intervention side of the natural cycle is. So in each cycle, we'll look at what the natural processes are and also what the impact of human intervention is on that. Carbon cycle is too simple, so I talk about it. So producers, carbon fixation, we talked about it. The plants, they take carbon dioxide from the atmosphere, so photosynthesis, and then they also release carbon dioxide in the process of respiration. So that's one natural process where carbon is fixed from the atmosphere into the plants. Eventually, all the life forms like us, the plants, when we die and when we decompose by the leftovers, that carbon goes back into the soil or goes back into the environment. And similarly, the forest fires, which also happen naturally because of fuel burning, which is a lot of anthropogenic activities, but naturally from like volcanoes, etc., there's a lot of CO or methane emission that contribute to the overall carbon cycle as well. So it's all of those processes combined. And if you look at, and you can also look at the human interventions into of how some deforestation, some forest fires, some increase in transportation and burning of fossil fuel is increasing the carbon content. Last time, that's right. And let's quickly also get to nitrogen cycle. And I think this also is pretty simple. It's also something that we all studied of how the N2 in the atmosphere is not reactive, but because of the electrical storms, that nitrogen can be converted into ammonia, then ammonium, and then nitrate, nitrite, and eventually back to nitrogen. And so the nitrogen is fixed, and bacteria have the most important role to play. So in nitrogen cycle, you cannot neglect what bacteria is doing. All of that nitrogen is essentially fixed by bacteria, which are the nitrogen fixing bacteria like Nitrosomonas and Nitrobacter, and then they fix it, the plants take it up, we eat it. So that's how that nitrogen, which is important for our DNA or our RNA molecules, is eventually fixing for us. I've also put the pollution part on the side for you to remember that how the same processes also contribute to pollution of the atmosphere. But just look at the interactions. So it's the land, air, water, and light. So between all the spheres of the environment, this is essentially cycling and recycling back. The processes are, so when you look at it, you hear things like ammonification, fixation, denitrification. It's just some of those processes that happen. And if we have time, let's quickly just look at the phosphorus cycle as well. So phosphorus cycle is the only cycle that does not include the atmosphere. It only includes the biosphere, the geosphere or the lithosphere, and the hydrosphere. So these three spheres are involved. It's a sedimentary cycle, it's not a gaseous cycle. So it comes from the soil. Like I said, it's the most slow of all, but phosphorus is the limiting. We need it for the growth of plants and essentially for eventually for our ATP production, which gives us energy for survival. And that phosphate is then, it comes to the water body, and so life on the water stays, not just the life of the plant. Yeah, so I think that's pretty much it. The only thing that I forgot to mention with nitrogen and now is true for phosphorus is the fact that we are increasing these components into the environment. If you remember nitrogen, which is nitrates that the plants and animals will take up, and phosphates in the case of phosphorus. When they increase in the environment, eutrophication. Let's also go back to the study. It's because these nutrients are limiting, and as soon as their concentration increases, then we have problems like eutrophication. Just the last one, Nadia, then I'll hand it over to you. Sulfur cycle is again like a lot of dimethyl sulfide bacteria again have a lot to play, but this too is a gaseous cycle, so it involves all the spheres. But sulfur also is produced naturally, so volcanic eruption, conversion of fossil fuels, human intervention, and then these bacteria that produce dimethyl sulfide, they then produce sulfur dioxide in the atmosphere, which turns into sulfur dioxide, which can then be converted into H2SO4, so that H2SO4 coming down again is basically just the sulfur cycle. So everything we've studied will emerge in this for you. The only thing that I wanted to say before we go to the quiz is, and I gave this assignment last time, and I was hoping that today we'll do this exercise in class, is that these cycles are not happening in cycles. Right now, if you look outside, all of these cycles are happening simultaneously. Although we cannot see it, but the sulfur, the carbon, the phosphorus, all of it is essentially recycling into the environment. And I want you to, when you go out, just think of how that's happening in the environment that you live in. A reminder that for lecture 5 and 6, where you have to go back to read chapter 15 and chapter 3, just the relevant components are not expected to be chapters. And Nadia, have you published the quiz? Okay, then let me quickly, maybe you can open your devices, log in.